Hello everyone and welcome. In this video I'm going to be explaining variable geometry turbochargers. Now in order to understand these you're going to want to already have an understanding of turbochargers, so if you haven't yet watched my video on turbochargers I'd recommend watching that first. Now variable geometry turbochargers are a very cool device which basically what you're trying to do is maximize the amount of boost you have across your entire rev range. So at low RPM you're not producing a lot of exhaust gas, so you're not going to have your turbo spooling very quickly unless you have a very small turbo, whereas at higher RPMs, if you have a lot of exhaust flowing, you're going to spool up your turbo very quickly and you're going to be able to provide a certain amount of boost. Now, when comparing turbochargers, one thing to keep in mind, one way of kind of comparing them is the AR ratio. And this is a ratio of the area of the exhaust inlet, basically how it comes into the turbocharger, versus the radius of the turbine. And the way that you can use this is basically looking at two different types of turbochargers. If you have a turbocharger with a very high AR ratio, then basically what that means is you've got a very high flow capacity. It'll look something like this as it enters into the turbocharger. So what this does is at very high RPM, when you're creating a lot of exhaust, you need a large space to fit all that exhaust through, and it's capable of very high boost because it's capable of such a high capacity of gas flowing through it. The problem with this is you're going to have turbo lag, because at low RPM, when you don't have that much gas coming through this, it's going to be moving fairly slow because there's so much space for it to move through. So what you can do is take a smaller turbocharger which has a lower AR ratio, and that squeezes the gas further down so it has a smaller space to go through. So what this does is it increases the velocity of that exhaust gas traveling through there, which means you can spool up your turbo quicker since you have that high velocity gas hitting the turbine, and then you can have boost at low RPM. The problem with this is once you get to higher RPMs, only a certain amount of gas can flow through this, so you can only supply boost at lower RPMs. Otherwise you're not giving enough air to the engine, and the boost starts to drop down as you require more oxygen for your higher RPMs. So what does a variable geometry turbocharger do? Well, it takes the best of both worlds. It combines these two into a single turbocharger, which is why they're so awesome. So what happens is, when you're at a low RPM situation, you've got these vanes inside of the turbocharger, and these vanes are on pivot points so they can adjust. So here's your turbine, and here's these vanes, and then here's your incoming exhaust gas. And this is going to be a scenario where you're at low RPM. So as that exhaust comes in, it's squeezed into a very tight space between these vanes, and thus it gets a large velocity, and it forces this turbine to spin and provides adequate boost for the engine. So basically what the flow is going to look like is this lower AR here, like we've got here, so a high velocity. Now once you get to those higher speeds, you can't squeeze all that air through here, so the turbocharger basically starts to stall out and it can't keep up with all the air that you're trying to put through it. So what this does is as your RPM increases and your exhaust flow increases, these vanes slowly begin to rotate open and open up like this. So here you can see the path the exhaust gas takes versus over here is much wider. So it's changing the AR ratio, and you're allowing for a greater capacity of air to travel through this turbo. So what that does is it gives you more air to put through the turbocharger. You need more air because you're at higher RPMs, so your engine cylinders are firing more often. They need more oxygen to do so, and that's satisfied with this condition. Now, how do these vanes inside of the turbocharger move? What actually makes these rotate? Well, here we've got basically a look at what's going on. So these vanes are on fixed points within the turbocharger, and they're actually inside of it. Now outside of the turbocharger, you're going to have this ring which all these vanes are going to be basically connected to. So you're going to have these vanes on a fixed pivot point. They're going to be connected to this connecting link, and that connecting link is going to be connected to a bearing on this outer wheel here, which is going to rotate. So this disc that rotates here is connected to an actuator, a linear actuator, and this linear actuator can pull this and this in or out right here, and that's going to force this ring to rotate. Now if you don't know how linear actuators work, I've got a video explaining several different types of actuators. You can check that out. I'll put it in the video description. And you can use various types of actuators here. But basically what's going to happen is you're going to rotate this ring, and as this ring rotates, these connecting links are going to move with it, and they're going to spin that vane there on its fixed pivot point. So you can see here, this is a situation in which the vanes are all opened up at a higher RPM, and then if you're at a lower RPM, you're going to have these rotated inward. So if this linear actuator were to push itself outward, you're going to be slowly opening up those vanes and allowing for more exhaust to flow through the turbocharger. So this, like I said, isn't directly inside of the turbine. That wouldn't make any sense. So if you're looking at the turbocharger from the top, this is basically what's going to look like. So you've got these vanes inside of the exhaust side of the turbocharger, and then they have these little connecting points which send them back to this disc, which is outside here, and that disc is what rotates, thus pivoting these little vanes inside of the turbine. So ultimately, what is this achieving? Well, you've got boost versus RPM, and with a fixed AR ratio turbocharger, basically you're going to optimize it for a certain rev range. So this one here, for example, you get to a certain rev, and it creates the maximum boost, and then it kind of dies out as you go on. Well, with a variable geometry turbocharger, you can maximize for a much greater RPM range. So it's going to get boost quicker, and then it's going to keep that boost longer, and it's going to have a much wider rev range for which you can have maximum boost, thus having maximum torque and maximum horsepower for that rev range. So thank you for watching. If you have any questions or comments, feel free to leave them below.